Hi everyone. I wanted to show you a couple of things that'll help you finish and debug Project 4. The first thing I want to talk about is the tri-state wire, or the high Z you might see. So here I have the beginning of Project 4 loaded up, and you can see the wires look normal here. They've got zeros on them and whatnot. But if I go to start simulating the CPU and I take a step, you'll see that this wire coming out of the instruction memory turns blue. And if you point at it, it has a value of high Z, which stands for high impedance. So let me show you what that's all about. So if we go inside the instruction memory subcircuit, there is an actual RAM element. That's this memory element here in JLS. And this element can be turned completely off. If we were to put a 1 on the CIS input down here, that would mean turn this chip off. And so when you turn the chip off, there is no output at all. It's as if that wire were just sticking up in the air, something that we technically call a high impedance state. This concept of high impedance is important to electrical engineering, but we don't really touch on it here. And so for the most part, you can treat high impedance as a 0. It doesn't really matter much to what we're doing, except when it causes problems. So if you're not having problems, and you see a blue wire or you see a high impedance value, just ignore it. On occasion, you'll run into problems where JLS will say that you can't connect a regular wire to a tri-state wire. A tri-state wire is just a wire that might have that high Z value on it. So here's what you do. You take this output from the instruction memory and you delete it. Once you delete it, then these wires all revert back to normal wires. You may have to save and reopen your circuit, but when you do that, those wires should all be black again and normal. Everything should let you connect up. And then once you've connected everything up, then the very last thing you can do is put that wire back. And when you put that wire back, put it back right to left. First, connect it to the main part of your data path, like the instruction wire here on the right, and then drag the other end of the wire over to the source of the high impedance, in this case, the output of the instruction memory. You may have the same issue with main memory here, because this chip can also be turned off. So again, if you have to disconnect the wire, connect it from the right, and lastly, connect it to the output of that main memory. That should make all of those weird high Z glitches go away. Next, I want to show you how to debug your CPU. The basic approach to debugging your CPU is to take machine code and insert it into this instruction memory. And then you can use the simulator to step through your CPU one cycle at a time and see that the correct instruction is loaded and the correct values are making it to and through all the muxes. So just for point of reference, if you right-click on this instruction memory and click Modify, you can see that you can either add data right to that instruction memory, so you could type the machine code right in here. Nothing wrong with that, but there's an easier way to do it. Or you can specify a file that will contain that machine code. And so I have it already set up so that that file is named instructions. Notice the lowercase I. So you don't have to mess with this. I just wanted to show you how it was hooked up. What you want to do instead is pick the assembly code that you want to step through. So for example, maybe we'll take the basic ops demo test that you're provided in the starting code. And then you want to use a program called Mars Assembler. So you can run Mars Assembler. You give it the name of the assembly code you want to step through. And now if I just run it like this, I see that I forgot DL unit. So let me grab that quickly. Okay, so now if I run Mars Assembler, what you see is that it spits out the machine code. This is the machine code here in the second column. And so JLS expects memory contents to be specified in two columns. So the first column is the word address, and the second column is the content. So at word address 0, there's the instruction. Word address 1, there's the instruction. Word address 2, there's the instruction. The hash means there's a comment. So what you can see to the right of the hash is the actual address where this would appear in Mars, and the line of assembly code that produced that machine instruction. Now we don't want this on the screen. Where you really need it is in the file named instructions. So I'll redirect that to the instructions file. You can see that it is now in the instructions file. And so with that data in the instructions file, JLS will automatically load that when we start to simulate the CPU. Now, when I'm debugging, I find it most useful to set my step here to half the length of my clock cycle. What that lets me do is see the state of the CPU at the beginning of the clock cycle and halfway through it. You may be just fine stepping through the whole clock cycle. You may want to see smaller pieces, but halfway through is a good starting point. So I'll set this to 2500 and I'll step through. And now you can see that coming out of instruction memory is that machine code. And then you'll have more of this wired up, but you can trace the various parts of that machine code through the CPU, and you'll also be able to look at the control wires. So we know that this first instruction is an AND I, so I'll just drag a wire out here. And so we can see that for an AND I, my control unit is giving a 1 for ALU source, which it should. Here it's giving a high impedance for the branch instead of a 0. But again, like I said, if it's not actually causing problems, just treat that as a 0. And so that's how you can see that your control wires are set properly for the instruction and how the data flows through the different components. Okay, so hopefully that helps you avoid some of the common problems and also helps you easily get up and running when it comes time to debugging your CPU. Okay, I also want to say a few minutes about byte addressing and word addressing. That tends to be a point of confusion for this project. Thus far, we've been working with a model of a byte addressable memory. So we have RAM, and we've been saying that it has 2 to the 32 bytes, which is 4 gigabytes. And we've been able to address each of those bytes individually. That's what we mean by a byte addressable memory. So to do that, of course, we need a 32-bit address bus. So with those 32 bits, we can identify a single one of the 4 billion byte addresses in our 4 gigabyte address space. But that's a little bit of a convenient fiction because, as we discussed in the cache video, RAM is actually far away. It's a bus trip across the motherboard. And so for the same reason that you don't typically go to the store and buy just one item, you don't typically go to RAM and grab just one byte. If you're taking that trip to RAM, you're going to bring a lot of data back with you. It's just more efficient. Now, MIPS abstracts this away by letting you ask for an individual byte by name and then going and getting whatever batch of data it naturally gets and throws away what it doesn't need. However, other CPUs make you ask for the specific chunk of information, not an individual byte. So we call those word addressable. So let's say, for example, that the CPU will grab data in chunks of 4 bytes. So our memory will look more like this. It'll be shorter and wider, and the bytes will be laid out something like this. Byte 0, 1, 2, and 3 will come as a chunk or a row, and then 4, 5, 6, and 7, and so on. So now, instead of numbering the bytes individually, we're just going to number the rows in this conceptual array. So this would be word 0, this would be word 1, this would be word 2, this would be word 3, and so on. So now, if, let's say, you wanted byte number 6, you couldn't directly ask for byte number 6. You'd have to ask for word 1, and then you would be responsible for pulling byte 6 out of that yourself. And this is the model that JLS goes with. When you ask the JLS RAM element for data, you can't ask for a specific byte, you have to ask for a specific word or group of 4 bytes. So what's going to come out of the ALU in your CPU is a byte address, and then before it goes into RAM, you need to convert it from bytes to words. The other thing about memory, while I'm on the topic, is the RAM element in JLS is only set up to use 2 to the 20 words. Now, of course, it could be as big as 2 to the 30 words, but that would create a data structure that's unnecessarily big, and since that number bumps up against the maximum size of an int, sometimes weird things happen. So I just created that RAM element to hold 2 to the 20 words. So after converting from bytes to words, you'll have a 30-bit address, but the RAM element is only going to take a 20-bit input. So what you do is you just throw away the 10 bits you don't need. And throwing those bits away won't be a problem as long as they all remain 0. So that just means don't write any programs that use more than a megabyte of memory, and then those addresses will all have zeros on the most significant 10 bits, and it won't matter that our RAM element isn't that big. Now, if you're playing around and you need a bigger RAM for some reason, just delete it and recreate it with more space. So hopefully this makes that first phase of the project just a little bit easier. As always, send an email or stop by my office if you run into any trouble.